All right. So, yeah, as Maria said, I'm Malcolm Barr. I'm the head of faculty for maths at St John's College, and I started teaching over 20 years ago. I did have a break, like a lot of young teachers. I did far too many things in my first few years and got burnt out. So I took a break and then got back into it, and I've been at St John's for 10 years. And it's an all boys school. It's a state integrated school, so that means we're not private. We in the old system we were a decile 7, but we take students from all over the Waikato, and we have some students who like when I was a dean, I had one student who was came from a family that had so little that he always left home at about 6:45 in the morning, because that way he got up and ate breakfast and then left before he got in trouble for eating the only food in the house. Through to students who come from um, the horse racing industries and things like that. So we have a huge range of students. So we're real cross section of society in our school. Um, so I got interested a few years ago in more research-based education, and I'll get a little bit more into that soon. But I just felt like what I was doing in the classroom wasn't quite right. It wasn't working the way it should. And from that came this. So what I'm going to talk about today, first of all, why I'm interested in cognitive load theory, and then I'm going to go through human cognitive architecture, the way our brain works in terms of learning, some of the cognitive load, and then I'll go into cognitive load theory effects, and then lastly I'll talk about how you can implement some of this in your classroom. So my inspiration that got me interested, I'm a runner, and I listen to podcasts and I read books. So the first book I bought was the one there by Craig Barton, How I Wish I'd Taught Maths. And if you haven't read that book, that is the first maths book you should buy. He lays out every chapter and what he used to do, um, why that doesn't work, and what he does now. And it's really, really clever. I think he'd been teaching about 12 years when he wrote that book. Really clever book. And then you see there's two other books there. The yellow one by Greg Ashton, Cognitive Load Theory, is a pretty quick and easy book. The Cognitive Load Theory in Action by Oliver Lovell is a bit of a deeper dive. Craig Barton does a podcast, and it was in there that I first heard about cognitive load theory and went further into it. So the podcasts that I listen to a lot of are these three here. Mr. Barton's Maths podcast, so that's the same Craig Barton that wrote the book. Education Research Reading Room, that's Ollie Lovell again. And then Chalk and Talk with Anna Stocky is from Canada. And all three of these, particularly the Education Research Reading Room and Chalk and Talk, are based on research. So Anna Stocky, she interviews researchers. The Education Research Reading Room with Ollie Lovell, he tends to do a whole lot of reading and learning himself, and then he summarizes that in a podcast about once a month, and he often has some top researchers in education. And so from that, I sort of developed this idea that everything you do in the classroom should be backed by research. Now that's a lofty goal, and obviously we're not ever going to fully meet that. But if we're always thinking, what can we do? Well, what are we doing, and does the research support this? So one of the things I used to do a lot of is if you had questions on the board that students had been working through, you'd then maybe get 5 or 6 of the students to come up and put their answers on the board while everyone else watched them do it. And it feels like you're doing really good things because you're engaging the kids and all of that. But in reality, I don't know that we've got any research that shows that that's going to be helping with learning. You've got 6 students coming up to the board and 20 something students sitting there doing nothing. If they get the answer wrong, are we reinforcing wrong answers when they write it small so other students can't see it? What's that doing? Really, what we're doing is we're using time, and no one's benefiting from the use of that time. So I got rid of that, and that's just one example of the many things that I was doing that I couldn't really say that they had a good learning outcome backed by research or by my observation of them. So that's where I'm going with all of this. So human cognitive architecture. Uh, when we think about this, I'm thinking about the way in which we learn. So there's lots of things we do that aren't involved with learning that are cognitive skills, but I'm particularly thinking about how we learn. So all information that we learn can be categorized as either biologically primary knowledge or biologically secondary knowledge. So primary knowledge is the things that we have evolved to know. So being able to listen, being able to talk, um, being able to walk, being able to eat, being able to swallow without choking on our food, all of these things, which are actually quite complex skills, but we all learn them as kids, and we don't really get taught them. We don't get taught how to swallow, we don't get taught how to walk. It just kind of happens. And these are the things, if we don't have them, we can't function as a human. So this is the primary biological knowledge. Um, and then the secondary knowledge is the stuff that we are taught. And that's basically everything that we do in schools is secondary knowledge. So schools were invented because people needed to learn biologically secondary knowledge. It's domain specific skills such as reading and writing and science and maths. So the skills that we learn as biologically primary, we pick up without someone teaching us to do that. The skills that we learn as biologically secondary, we have been taught by teachers, and the confusion that has happened in the decades long arguments that happen is with a discovery or inquiry learning is the idea that if we can learn all of this biologically primary knowledge without someone teaching us, then we should be able to learn our biologically secondary knowledge the same way. But in actual fact, our brain is not wired to do that. We haven't evolved to learn how to do reading and maths, but we have evolved to learn how to walk. And that's essentially where the problem is. So the idea of discovery learning simply doesn't work if you subscribe to this theory that I'm looking at here. That's not to say that constructivist approaches to problem solving don't have their place in the classroom, because they do, but we need to have the skills in our domains, whether it be in terms of maths or reading or writing, before we can dive into constructivist approaches to problems. So the cognitive load theory is concerned entirely with how we obtain that biologically secondary knowledge. We're not interested in the primary knowledge at all. So from here, let's talk about some memory models. So in memory, we can effectively think of having two types of memory. There's a working memory and a long-term memory. And for those who know about computer architecture, if you think in terms of RAM and hard drive, it's similar, not the same, but it's a similar way of thinking of it, where your working memory is your RAM. It's the on-call stuff that we can tap into immediately, and the long-term memory is kind of like the hard drive. So we are ignoring in this some other types of memory, like some sensory memories and things like that. I'm really only thinking about the stuff that we learn within school. So working memory is where all of our thought and our processing happens. And we used to think that you could hold about 7 things in memory, but in actual fact, research shows that it's about 4 things you can hold in memory at any given time. And without any repetition, you can only hold those things in your memory for about 20 seconds. And we like to think that we can do more than that, but if we get told a phone number, we tend to repeat that phone number over and over and over to keep it in our head. If you're just told the phone number, you will ditch that within just a few seconds. In fact, if you're just remembering it as the 7 digits or 8 digits of that phone number, you'll forget that within, you won't be able to hold those 8 digits. So you won't even last 20 seconds with it. So our working memory is actually very, very limited. Our long-term memory, on the other hand, is effectively limitless. If we can store things properly into our long-term memory, then we will remember them and have access to them forever, and we can put as much in there as we like. You only have to look at the people on the chase, on the quiz there, to see just how much information they can store. So it's not like a library that gets full of books. It's like a web of connections that just keeps growing and growing and growing. And once we've got stuff into our long-term memory, then we can retrieve it into our working memory whenever we want, and we effectively make our working memory become limitless because we just keep grabbing stuff and then putting it back into long-term memory. So the way this is all stored in our memory, the theory is that it's stored like a schema of information. So we can see here a schema based on marsupials, and you can see the platypus is up on the side because it doesn't really link to the other things because it's such a weird animal. But you can see the way that other things are linked in there with strong connections and weaker connections. And the more connections we can make, in our memory, the more we're able to recall these things and link them together, and our memory works even better. So we're always trying to link new knowledge to existing knowledge, and that's the way our long-term memory will grow. So if we look at it in terms of what learning is making changes to our long-term memory. So new learning comes into our working memory, and you can see there's a small arrow there that moves that into our long-term memory, and the long-term memory I've got described there as being huge. And then when we retrieve it, you'll notice I've got a much bigger arrow on the retrieval, and that's because we can retrieve things as much as we want from the long-term memory back into our working memory to use it. But getting it from working memory into long-term memory, there is only a very small arrow, because that's actually a really, really hard job. And if we do a more complex picture of that, we can see the environment, which is the things that we're looking at, the things we're listening to, the car going outside past the window, all of that, that's where our attention is. That's coming into our working memory. We're trying to learn that, getting into our long-term memory, and then you can see it comes back around, remembering it, and eventually things in long-term memory, in theory, will be forgotten if we don't access them long enough after some time. If anyone's got any questions along the way, throw them in the chat. I can't see the chat on what I've got here, but Maria can interrupt me if I need to be. It's so weird talking to a group that you can't hear any sounds. I'm not used to it. All right, so in our memory, in our learning, getting things from into our working memory and into our long-term memory, we basically have two types of load. There's the intrinsic load and extraneous load. So the intrinsic load, this is the stuff that is intrinsic to what we are learning, the things directly related to it. Everything else is extraneous load. So things like I said, the car going past outside, if that's taking up a wee bit of space in your brain, that's an extraneous load. And so if we look at that in terms of how that works inside that working memory, we have intrinsic load, we have extraneous load, and then we have a remaining capacity. And our working memory is limited. So what we want to do when we're teaching students and when we're trying to learn something is we want the intrinsic load to be maximized and the extraneous load to be minimized. And we actually want that remaining capacity to be minimized as well. Because if we have too much remaining capacity, then that's where our brains take off and start thinking about other things, or the students' brains do. So you want to be filling up intrinsic load as much as possible, but as soon as you overload it, then you might as well stop doing what you're doing. So what I'm going to do is I'm going to get you to do a little exercise here, and this is where you're going to put some answers into the chat if you take part in it. So I'm going to give you some time to remember these letters in order. All right, I'll give you about 30 seconds from now. Don't cheat and write them down. All right, and that's about 30 seconds there. So I'll hide them again. So what I'm interested in is how many people were able to remember all of those letters. See if you can write them down, see who can remember. And once you've done that, pop in the chat how many letters you got, and we'll check. Then I'll put them back up and you can check how many you got. Don't read anyone else's before you write them down either. A couple of people have put that up. All right, so these are the letters here. How many people got them right? GFOMNI. There's a few of them. Some VTR, and that was a WTR. That was a pretty good one. Jared's done well there. All right, pretty hard though. Okay, what I'm going to do is I'm going to show you there was actually, I think, 30 letters on there. I'm going to show you the same number of letters again, and I want you to see if you can do the same thing. See how many of these letters you can write down after looking at it for 30 seconds. Here it goes now. All right, that's 30 seconds. See how many you can write down, how many of those letters. Oh, Beverly's done well. Who's that? B Siny. You've only missed one of those words, so you got all but three of them. All right, so here's what they were. Same number of letters. We're going to do it once more. Oh, who was that? Sharon. Block the. Oh, you haven't got them in the right order. All right, let's see if you can remember this last set in order. Same number of letters. You got 30 seconds. I'm going to cut your time off there anyway. You don't need 30 seconds for that one. See if you can write those down. Yeah, good. So basically what happened there is we were looking at element interactivity. So when I put the first slide up, there was, I think it was 30 letters from memory. Uh, each of those you have to remember individually because they mean nothing to you in your brain. When I put the second slide up, you were seeing about 8 or 9 words. And so you're no longer having to remember 30 individual letters, you're just having to remember 8 or 9 words. But as I said, our working memory can really only store about 4 things. So the people who got to 7 words, that was really, really good. You probably were repeating them in your head as you read them over. And then for the last one, the same number of letters, but it was a sentence that you would have recognized or most people recognize. So you don't have to learn anything other than one sentence. It's effectively one thing in our working memory. So the number of elements in the first one was 30. The number of elements in the second one was about 9. And the number of elements in the third one was one single element. So that's why our working memory could cope with that so much better. And so what we're trying to do is we're always trying to reduce the number of elements that a student needs to see at any given time, or at least not overload them. We should always be considering how many things are we showing a student that are new elements because their working memory is so limited. And every time elements interact with each other, or the more elements we have, we are increasing the load, the intrinsic load, and sometimes the extraneous load if we've accidentally introduced elements that we don't want them to see as well. So if I show you this example of an equation, this equation is pretty straightforward to maths teachers. 4x plus 5 equals 17. But to a novice learner, to someone who is, say, a year 4 student, they would wonder why there's an X in there altogether. They would have never seen that. For someone who is beginning algebra in year 9, they might see the 4 plus 5 equals 17 and be reasonably familiar with that and not have a problem with that, but the X would cause them a big problem. And then we're going to show them that it's actually 4 times X. So there's a hidden element in there as well. And then if you were to show this to, say, a year 12 or year 13 student who is doing well at maths, they would look at that and they would very quickly see that and it wouldn't overload them at all. There'd be no problems for them. So we have to think about where is the student in their learning in terms of how many elements they're seeing. For some students, they're seeing, 7 or 8 different elements in there. For some students, they're effectively seeing that as one element like our sentence because they're very good at their maths. So that's the thinking around our memory, how our working memory, our long-term memory works, and trying to get things from the environment into our long-term memory. That's effectively our learning, making changes to our long-term memory. So we're going to look at the cognitive load theory itself now. It's basically a series of instructional recommendations built upon that knowledge of how humans learn, the knowledge of how humans get information through working memory into long-term memory to make that change there. So we're going to look at the effects. Now, there is a large number of cognitive load theory effects. I'm just going to look at 4 of them, which are particularly important to us when we get started on this. But if you want to have a deeper dive, you'll find that there's lots and lots more. And then we'll go through some practical classroom applications of these things. So the first one is the redundancy effect. Now, the redundancy effect is one that we see all the time, and we see it in every classroom that you'd ever go into. It's one that we can't get rid of completely. So the redundancy effect is basically saying that any information that is extraneous or is a duplication of already existing information is taking up load in our working memory that we don't want it to. So some of the examples of this, the most easy one is posters in your room. So if you go into a geography classroom, guarantee in the geography classroom you're going to have posters all over every single wall. I find it really claustrophobic anyway, but if a student is sitting in that classroom trying to learn something that you're potentially putting on the whiteboard, they have a whole lot of information all around the board, all over the wall in front of them, which is filling up some of their working memory. Even if they don't think they're looking at it, just the fact that it's there with those words and those pictures, it's going to be taking up some of their working memory. Another redundancy effect that students will always argue is that when they listen to music, it helps them learn. But the mere fact that you have music going in your ears means that your brain, at the very least, is having to discard that from its thought. And that's using a little bit of working memory. So anytime they say that the music is helping them study, it is not true. It is taking up space in the brain, and the research does show that. And then the other one, which I think is really interesting, is the written and spoken information at the same time. So one of the things that we do a lot as teachers of maths is when we're doing worked examples or something like that, we might be writing our example on the board, and at the same time we're saying what we're writing down. Or you often see it when you're in staff meetings and the deputy principals, well, I wonder if the listening to music research applies to all students. I see neurodiverse. I'm not going to comment on that because I don't know. Someone says, is it, if for some neurodiverse students, it isn't so true that music may help them. What it may do is it may help them to, I think, probably get rid of other distractions. So if there are other distractions that are causing more of this redundancy effect than the music, then that's probably a fair statement. Yeah, the written and spoken information, I was about to say when we're in a staff meeting, and deputy principals for some reason do this a lot, where they put a slide up on the screen and then they will read you the words that are on the slide. If you're reading those words yourself and are speaking them, then you are processing two pieces of information, even though they're the same information. And that creates a redundancy effect as well. We're using up two parts of our brain because we use different parts of our working memory to process information coming in auditory and information that we're coming through visually. So we need to make sure that we're not doing that. All right, the next effect that I want to talk about is the worked example effect. So this is the most well-known effect, and it talks about the way in which we should be using worked examples to help with learning. And we all know that worked examples, particularly in maths, are going to help us. What we don't realize is how little change there should be from one worked example to the next. So I'm going to suggest here that we should do a lot more worked examples than we currently do and alternate with student practice. So the common view of the worked examples on the left there is that the teacher models a worked example and then the students practice similar examples. Sometimes the teacher might do a couple of worked examples and then the students practice them. With cognitive load theory, then the teacher should model an example and then the student should practice the worked examples. And you'll see there it says alternating or fading. What we should be doing is we should be going backwards and forwards between the teacher doing a worked example and the students doing a similar problem. And the fadings is talking about how we can reduce the amount of work that we put into the examples that prompts them. So they're getting more and more towards doing it all on their own. If we look at this another way, we can think of it as alternating, and each worked example may get slightly more abstract. We might leave more out of the worked example before the students do their similar problem. This was something that took me a long time to implement properly in my classroom because it felt really weird. I was spending a lot more time on worked examples, but once students got off onto their independent work, I found that they were much more likely to be able to do it without me having to go over things that I thought I'd already covered in worked examples. So I went from doing 2 or 3 worked examples to sometimes doing up to 10 worked examples on a single task. but then when they worked on them themselves independently, they didn't need nearly as much practice time as they had done previously. The next effect here is the expertise reversal effect. I'm not going to spend a lot of time on this, but it's just the knowledge that as students or as people become more expert, then we need to move away from the worked examples and need to fade out those worked examples. Because what happens is if our worked example has too much information in there, or we're slowing down students who have already got to a point, then we actually hinder their progress. So as they become more expert, we need to allow them to do more of the work themselves. It would be the same as that the quick brown fox jumped over the lazy dog, trying to teach them that letter by letter. It would slow you down significantly. Right, the next one we're going to look at, split attention effect. Now, this one is often very much misunderstood, and people describe this one as the same as redundancy effect, because they're thinking of someone who is looking at the work and their attention is taken by a poster or someone else talking in the room or something like that. But in actual fact, the split attention effect is in terms of how information is presented. So if we look at this geography type poster here, and I don't know geography at all, but I can see there that there are 4 different parts of that poster, and they're labeled 1, 2, 3, 4, and underneath are the names that go with it. Now, for a student to process that, they need to look backwards and forwards between the picture and the words. But if it was presented to them like this, it's much easier for them to understand. And the amount of working memory used to do that is far less. So if we can put things that belong together on a diagram, then the cognitive load is far less to do that. And this is something that we should be trying to do in maths a lot. So if we look at this one here, the picture on the left, in fact, it's the same problem. The solution is drawn, if we do it as a worked example, the solution is written underneath on the first one, and on the second one, the solution is written into the diagram, showing where those bits of working belong. If we were to show this as an example to our students, and if we were to get them to work on a problem like this by actually drawing into the diagram, it means giving them a larger diagram. They're going to find that they can get through this much easier because they're not having to look backwards and forwards between the diagram and their working, which is creating that split attention effect. So those are the 4 effects that I want to look at, and then from here in the next few minutes, I'm going to go through how you can implement some of this within your classroom. So hopefully some of the things I'm about to tell you can take away, and you can put them into practice in the coming week. I would recommend not trying to do everything in one go. Pick 1 or 2 things and see if you can do that first of all. So the first thing is reducing the number of elements, and I use this phrase here that we write a shopping list not to remember but to be able to forget, and hopefully some of you have heard that before. When you go to a supermarket, if you don't have a list, you're not going to come away with the things you want. And the misconception is that we write the list so that we remember things, but we don't. We actually write the list so we can forget about it, and the list does the remembering for us. We just have to look at it. So we write the list not so that we remember, but so that we're able to forget. So in maths, we can do that by writing down the steps to a problem before we do it. And I do that with some of the more complex, say year 12 calculus work, where I get them to write down the steps to solve a problem if it's getting the tangent of an equation or something like that, because there's a lot of steps involved in that. We can also pre-teach vocabulary. So if we teach vocabulary before we use it, so words like coefficient, term, all those algebra words that students, they're trying to do so much already, and then we're using words they don't know. If we can pre-teach that vocabulary, then we're not using up working memory with an element which they don't know already. If they know the word coefficient, that's effectively not a new element. It's something that's coming from their long-term memory. We can break complex problems into steps, so that's the chunking, and that's exactly like those 30 letters that we did earlier. If we break them down into steps that they learn individually, and then we put them together, it's much more like learning those 9 words rather than the 30 letters. So if we were to learn each word individually. And then the last one, which I just mentioned before, is for NCEA questions. Write down what the question wants. I get the students to put down on those question papers where they're given a whole page to do their answers. Right at the bottom, they should write down what it wants. So if the question says, what are the dimensions of the garden? At the bottom of the page, they should write width equals, length equals. And then when they get to the bottom of the page, they're not going to forget to do that last step. Or if they're doing something like the tangent to a curve in year 12 calculus, if they write down a few of the steps like differentiating, finding the gradient, doing the equation, then they're far less likely to make mistakes because they're thinking of it in terms of the steps. They've got their shopping list there. The next thing we can do in our classroom is we can reduce redundancy. So the first one is silent teacher, and this is one that we all struggle with, or most of us do as teachers, is to actually just be quiet. I know that I am more often than not the most distracting thing in my room, and I have to work really hard not to be. And it's very difficult to just be silent when students are working or when we're putting worked examples on the board. But if we have a properly silent room, then it's easier because our silence will break that. And once you get that culture of silence in your room, you'll find it's much easier. But really think about every time you're speaking, is it something we need to be saying? The second one is the posters. I've moved all the posters in my room to the side walls and the back of the room. I think there's one poster about evacuation that I have to have on the front of the room, but everything else I've moved away. So there's nothing that is in the direct eye line of the students that I don't want them to be looking at. The third one is here from when I did this prior to the government's decree, but phones is a big one. I thought phones weren't a problem in my classroom. I thought no one was ever using them until our school made the rule not to use them during class time, and it actually made a real difference. Phones are so distracting. They need to be on silent. They need to be face down so that they can't see the lights from them and all of that. And I know that not all schools follow the rules as much as they should, but phones really, really need to be gone because they take up lots and lots of their working memory. And then the last one is to stay on task. I used to regularly dive off onto stories that were pretty irrelevant. Now when I do that, it is, and I still do because I like to tell stories. Most of us teachers do, but I do it at times where I deliberately do it. It might be towards the end of the lesson. It might be if I know the students have come from a big assessment earlier and they're a bit tired, we might take a break from the lesson and I might deliberately just go off on a tangent talking, but I know that I'm doing that and then I bring it back and we get back onto task. It's more of a break for their brains rather than me just interrupting to tell a story. So that's how we can do it with our redundancy effect. So what I'm going to do now is I'm going to show you a question from an NCEA exam a couple of years ago. And I want you to have a think about in this question, what sort of things here are adding to the cognitive load of students? I'm not sure. I think my face might be in front of the top of that. So two possible configurations of a house shape are drawn below. A house shape is drawn where C is at 0, 9, A, B are the points on that parabola y equals 9 minus x squared, and E and F are on the x-axis, and you have to find the height of the wall, which is either AF or BE, when the area of the house shape is a maximum. So just have a think. Feel free to chuck something in the chat if you can see something that you think is adding to the load of the students. My face is distracting. Thanks, Jared. I don't know how to turn it off now that I've got it on there. Yeah, label the parabola with its equations. Bang on. So we've got up in the top there, y equals 9 minus x squared. And so the parabola is the same in both of them. So if they were to write that on, if they were to say put that just there next to the parabola, then that would mean that the students can immediately see that y equals 9 minus x squared, and it could go in the same place there. What else have we got there that potentially is difficult for them? I think the same thing where it says C is at 0, 9, the coordinate value, that's right. So they could put right next to C here, they could put the coordinate in here. And if they did that, then both of those are the split attention effect. The other thing that they've got there is that they've got two diagrams showing the same thing. There isn't room to put the working for the room height. I think this is at the top of a page, and the whole page below was all lines. But I think what they should do is they should actually um, only have one of these diagrams, and next to A and B, they have me drawing with a mouse, which is always difficult. They could put arrows to show that A and B move along that axis to try and find where that maximum is. If they did that, then you wouldn't be looking at two diagrams. Students, when they first look at this, they wonder why they've got two diagrams. Um, and it takes a minute for them to realize that point C and the parabola are identical on both, and that the difference between the two shaded areas is simply that A and B have moved along the parabola. And if they were to draw that with one diagram, they would reduce that. So I think there's a bunch of things there, and we can also look at some other things that are on there. But those are the things that I would straight away say, if students were to write that on there. So if this was a class of mine looking at this, I would get them, first thing to do is basically scribble out that picture, and then fill in these details I've got here. And that way they're looking at a diagram where all of the information that's presented in the bullet points above is presented on the diagram. And then the next thing I would do is at the bottom of their working space, I would write the word maximum, and I would also write the word justify, because then when they get to the end of their problem, they're not going to forget to do those couple of things. Because the reason that students forget these things is their working memory has been taken up answering all the questions. They've gone through all of the steps of it, and they get to the end, and their working memory is completely full. And what they've actually done is they've worked out what the height of the wall is, but they haven't shown that it's a maximum, or they haven't justified it. Or, in fact, what they normally do is they work out what that maximum area is, but they don't say what the height is. Whereas if they write that down, so I'd probably get them to also put the word height at the bottom there, and maybe put some steps down as well. But I think that those things there, and this one question, you can reduce the working memory load significantly by taking a few steps before they start. And it would be really nice if our exam writers took that into consideration before they wrote it. And in fact, in the UK, there is a real there's a whole lot of work being done at the moment with the exam writers to do exactly that, to start thinking about how can they change the way they write the exam so that they're not introducing load on the working memory that just doesn't need to be there, and the questions actually become more about the maths. So it'd be nice if we had that. But anyway, that's a few things we can do there and showing it on a real question. So that brings me to the end of what I've got there. So if anyone has any questions or anything, that's the end of my presentation. I'll leave you on that slide there, actually, which are those books and podcasts that I talked about at the beginning.
Thank you so much, Malcolm. I'm just going to see if there's any questions and open it up.
Yep. Compartmentalization. How do you mean by that? Uh, yeah. Students, and this has actually been researched as well. If students learn something in maths and they learn something in science and it's identical, they can't see how the two are the same thing. They can't do that. And we actually worked on that in our school with the year 10s doing numeracy work for the common assessment activities, where we get teachers to explicitly talk about where things are the same, or where they're different, where sometimes some graphs in social studies, they talk about them in a different way to what we do in maths. So the teachers try to explicitly state that this is the same as you're doing in maths, or this is different because students don't see that. And the more that they do see that, the better the learning is, because they can apply that. Yeah. And it's a really hard one. It's a and I don't think they know why students do it, but definitely it's been studied that students cannot see that one learning is the same as another if they do it in different subjects, unless they're explicitly told.
Thank you so much, Malcolm. I just want to say that on behalf of everyone, I probably am similar to everyone. I have so many pages full of notes that I've written down and pictures. And as teachers, we run our class how we would from experience. So it's really nice that you're leaning into research and implementing it in this space. So thank you for sharing. Thank you so much for coming through to this space. I know a lot of us will start looking into these books and writing it down. But I learned a lot, and we've got some takeaways to place into the classroom.
My pleasure. Thank you.
Everyone, I'm just going to quickly share slides of in regards to feedback or any questions you might have. So hopefully this is coming through. Can everyone see that?
Yep, that's up.
Oh, cool. If you have any feedback, please chuck it in the chat or any suggestions for future sessions. Type in the chat as well or email amaonline.organizer@gmail.com, which is our lovely Jared in here. All the resources and videos will be shared next week. Just some dates that's coming up. The NZAMP conference, first week of July and the holidays. I'm doing exactly what Malcolm said not to do by reading out the slides, but I'm sure that's okay for a Saturday morning. Maths week is Monday 11th August to Friday the 15th of August, and I will practice what has been shared and give you about 10 seconds to read the last two bullet